Have you ever felt like gravity is off? Like you could jump just a little higher today.
Mm.
Okay, maybe not. But what if I told you there's a place on Earth where gravity actually is weaker? Like you would weigh a tiny bit less just by standing there.
Yeah, that's right. And it's not science fiction. It's a real place
Whoa.
in the Indian Ocean.
Okay.
It's called the Indian Ocean Geoid Low, or IOGL.
IOGL. It sounds mysterious,
It does.
but you're saying it's not like some supernatural thing.
No, not at all.
Right. It's
It's a massive gravitational dip.
huge.
Yeah, over 100 kilometers below the global average.
That's incredible. And it's a window into what's happening deep inside our planet.
Yeah, processes that are happening deep within the Earth.
So today we are diving deep into this invisible force field.
Right.
The IOGL
Mm-hmm.
will uncover what it is, how it formed, and what it tells us about the hidden workings of our planet.
Yeah, and what's really interesting is this low isn't something you can see or feel.
Right.
We only know about it because of some very precise measurements
No.
from satellites.
Oh, wow. So we have to understand what Earth's geoid is to understand the IOGL.
Yeah, you could think of Earth's geoid as almost like the shape that the oceans would take
Okay.
if it was only gravity acting on them.
Hmm.
So ignoring things like tides and currents,
Yeah.
that shape is the geoid.
Okay, so the IOGL is like a giant dip in this shape.
Exactly. It's like the deepest dip in this gravitational landscape.
Okay, so this idea of Earth's gravity varying across the surface,
Mhm.
that wasn't something we always knew, right? I mean,
Mhm.
Newton figured out gravity a long time ago.
Yeah, Newton's law of universal gravitation laid the foundation, but even he didn't have the tools to measure the subtle variations in gravity.
Right. He just knew that it existed.
Yeah.
He didn't know that it was different in different places.
Yeah.
So how did we go from Newton's apple to mapping these gravitational dips and bumps?
Well, it was a very gradual process. Early efforts to measure Earth's shape, like those by the French Academy of Sciences back in the 18th century, confirmed that Earth isn't a perfect sphere. It bulges at the equator and is flattened at the poles.
So not a perfect sphere, but still, how does that connect to gravity? Did they have like super sensitive scales back then?
Not quite. It wasn't until the 20th century that we had more precise gravity meters, that scientists started noticing areas where gravity was stronger or weaker than expected based on the Earth's shape.
Oh, interesting. So they had a model, and the model wasn't matching up with what they were observing.
Exactly. And these were the first hints that something more complex was going on.
But it was those satellites that really cracked the case, right? Those high-tech eyes in the sky that gave us the first detailed view of this gravitational landscape.
Exactly. Satellites like GRACE and GOC revolutionized our understanding.
Okay.
They could measure these minute changes in Earth's gravity from space,
Wow.
mapping the geoid with incredible detail.
And that's how they discovered the IOGL,
That's right.
the biggest dip
The most,
in the entire geoid.
the most dramatic dip in the entire geoid.
Wow. So we have this invisible valley in the Indian Ocean, but it's not just a random occurrence. It's the result of some serious geological drama, right?
Yeah, you're right.
I mean, we're talking millions of years of Earth's history here.
Absolutely. The IOGL is a product of deep Earth processes,
Okay.
a story of ancient oceans closing,
Oh,
continents colliding, and the slow, powerful movements of Earth's mantle.
okay, so let's fire up the time machine. We're going back to a time when the Earth looked totally different. What are we looking at?
Okay, so imagine a vast ocean called the Tethys Ocean, separating the supercontinents of Gondwana and Laurasia.
Okay.
These continents, driven by the forces of plate tectonics, slowly moved towards each other.
Yeah.
And the Tethys Ocean began to close.
Continental drift.
Yeah.
I remember learning about that in school. So
Yeah.
basically, the continents were playing a giant game of bumper cars,
Yeah.
and the Tethys Ocean got squeezed out.
Yeah, that's a great way to put it.
Right.
As these continents converged, the Tethys Ocean floor was forced under the Eurasian plate
Okay.
in a process called subduction.
Subduction.
Yeah, so imagine this dense, heavy slab of ocean floor
Yeah.
sinking into the Earth's mantle,
Okay.
like a rug being pushed under a door.
Okay, I can picture that. But how does sinking ocean floor lead to weaker gravity? It seems counterintuitive. You're adding more mass.
Right, it's not just about the sinking slab itself.
Okay.
Think about what happens when you drop a rock into a bucket of water.
Yeah.
The rock displaces the water,
Right.
creates ripples, changes the water's surface.
Okay.
So the sinking slab is like that rock.
It's pushing the mantle out of the way.
Exactly. The subducting Tethys Ocean floor pushed aside hotter, less dense material in the mantle. And this leads to what we call a mass deficit.
A mass deficit, so there's less mass.
There's less mass in that region compared to the surrounding areas.
And therefore less gravity.
And therefore gravity is slightly weaker.
Okay, that makes sense.
Yeah.
But there's more to this story, right?
There is.
There's another force at play.
Yeah.
Something rising to meet that sinking slab.
You're thinking of mantle plumes.
Mantle plumes. What are those?
So picture these as giant pillars of hot, buoyant rock rising from deep within the Earth. Almost like lava lamps.
Oh, wow.
On a planetary scale.
So you have these two opposing forces. The dense slabs are sinking and these hot plumes are rising. It's like a giant slow-motion dance.
It is.
Deep within the Earth.
A very accurate description. And these plumes likely rose up to fill the void left by the sinking slabs. So it's a balancing act deep within the Earth, this interplay of sinking and rising.
So over millions of years, this dance of sinking slabs and rising plumes shaped the mantle.
Yes.
And ultimately created the conditions for the IOGL.
Precisely. The IOGL isn't just a snapshot in time. It's a testament to the ongoing dynamism of Earth's interior.
Right.
A reminder that our planet is constantly changing.
Even though we can't see it.
Even in ways we can't see.
It's incredible how these processes happening far beneath our feet can have such a big effect. It's like Earth has a hidden heartbeat.
Yeah.
And the IOGL is one of the ways we can listen to it.
A poetic way to put it.
It's true, though.
But you're right. And to understand this heartbeat,
yeah,
we need to go beyond just observing the surface.
Right.
We need to see into Earth's interior.
Like an X-ray.
And that's where some truly remarkable technology comes in.
That's what I love about science.
Yeah.
It's like we're constantly pushing the boundaries of what's possible, finding new ways to explore the unknown.
Yeah.
So how do scientists actually see into the Earth's interior? It's not like we can just dig a hole that deep.
No, that's where seismic tomography comes in.
Okay.
A technique that allows us to create images of Earth's interior using earthquake waves.
Oh, so we're using earthquakes to see inside the Earth. How does that work?
So imagine you throw a pebble into a pond.
Yeah.
You see ripples spreading out from where it landed.
Yeah.
Earthquakes generate similar ripples.
Okay.
But instead of water, they travel through the Earth itself.
Oh, so we're using those earthquake ripples to map out the Earth's inside.
Exactly. By analyzing how those waves travel, how fast they move, how they bend, we can infer the temperature and composition of the material that they're passing through.
It's like mapping out a hidden landscape using sound instead of sight.
Yeah, that's a great way to think about it. And what's incredible is that seismic tomography actually supports the theory we've been discussing.
Oh, cool.
Yeah. The images show those cold, dense remnants of the Tethys Ocean sinking beneath the Indian Ocean, and those hot plumes rising up to counterbalance that density.
So it all fits together. Ancient oceans, colliding continents, sinking slabs, rising plumes, and it all culminates in this massive gravitational anomaly, the IOGL.
Yes.
It's like a detective story, piecing together all these clues.
It is.
To understand this invisible force field.
That's right.
It's pretty amazing.
Yeah.
And the story doesn't end there. The IOGL isn't just a curiosity. It has real-world impacts that we're only beginning to understand.
Yeah, that's true.
That's what we'll explore in the next part of our deep dive.
Okay.
We'll uncover how this gravitational anomaly affects the world above, from ocean currents to potentially even the climate. Stay tuned.
I'll be here. Welcome back to our deep dive into the Indian Ocean Geoid Low.
We've been on this incredible journey into the Earth's interior, uncovering this story of how this massive gravitational anomaly formed. But now I'm really curious, like, how does this hidden world, this IOGL, affect the world that we see and experience?
Yeah, that's a great point. It's easy to think of the IOGL as this abstract concept, this invisible dip in the Earth's gravitational field.
Right.
But it actually has some really tangible effects on the oceans, the climate, and even potentially the ground beneath our feet.
So we're talking about like the visible consequences of this invisible force field.
Exactly. Remember, the IOGL represents a mass deficit, meaning there's less mass in that region compared to the surrounding areas,
Right.
and therefore weaker gravity.
Okay.
And this weaker gravitational pull affects the very shape of the ocean surface.
Wait, so the ocean isn't perfectly flat? I always imagined it as this vast level expanse of water.
Yeah, it's a common misconception, but in reality, the ocean surface is quite bumpy.
Really?
If Earth were a perfectly uniform sphere with no other forces at play,
Yeah.
then yes, the oceans would form a smooth, even surface.
Okay.
But thanks to variations in gravity,
Right.
the actual shape of the ocean surface, what we call the geoid, is anything but flat.
So the IOGL creates a kind of dip in the ocean, like a dent in the water.
Precisely. Sea levels over the IOGL are actually several centimeters lower than in surrounding areas.
Wow.
It's a subtle effect, but it's there, all thanks to that weaker gravitational pull.
Okay, I'm trying to wrap my head around this. We have this huge gravitational anomaly in the Indian Ocean pulling down on the sea level, creating this dip. But does it actually have any noticeable effects? Like, does it change how the ocean behaves?
It does. It might seem like a small difference, just a few centimeters.
Right.
But even those subtle variations in sea level can influence the way ocean currents flow.
So the IOGL is like an invisible hand guiding the currents.
Yeah.
Like it's steering the water.
In a way, yes. Think about a ball rolling down a hill.
Yeah.
It naturally follows the path of least resistance, moving toward the lowest point.
Right.
Similarly, ocean currents tend to flow towards areas of lower sea level, where the gravitational potential is lower.
Okay, I'm following you. So the IOGL, by creating this dip in the ocean surface, can subtly nudge those currents in a particular direction.
Exactly. But it's important to remember that ocean currents are influenced by a whole complex interplay of factors.
Like what?
Including wind patterns, temperature differences, and the rotation of the Earth.
Right.
The IOGL just adds another layer of complexity to this already intricate system.
So it's like adding a new ingredient to a recipe.
Yeah.
Changing the flavor of the final dish. It makes the ocean's behavior even more fascinating, but also more difficult to predict.
Right, precisely. And this is where things get really interesting, because those ocean currents play a major role in distributing heat around the globe.
Right? They're like giant conveyor belts.
Exactly.
Transporting warm water from the tropics towards the poles and cold water from the poles towards the equator.
Right. They're crucial for regulating Earth's climate.
Yeah, they help keep things in balance.
Exactly. Now, if the IOGL is subtly influencing the flow of those currents,
Right.
even in small ways, it could have ripple effects on regional weather patterns
Got it?
and potentially even global climate systems.
Wow. That's pretty significant.
Yeah.
So this gravitational anomaly in the Indian Ocean could be influencing the weather on the other side of the world.
Yeah,
It's mind-boggling how interconnected everything is.
it is. And that's one of the reasons why studying the IOGL is so important.
Right.
It gives us a deeper understanding of these complex interactions between the Earth's interior, its oceans, and its atmosphere.
It helps us see the bigger picture.
Yeah.
It's like those nature documentaries where they zoom out from a close-up a tiny insect to reveal the entire ecosystem. We've been focused on this one feature, the IOGL, but now we're seeing how it fits into the grand scheme of things.
Exactly. And as we continue to explore the IOGL, we're likely to uncover even more connections.
Right.
Even more ways in which this seemingly isolated phenomenon influences the world around us.
So we've talked about the potential impact on ocean currents and climate, but what about the Indian Ocean region itself? Does the IOGL have any noticeable effects on the countries and communities that live around it?
Yeah, it's a question that scientists are actively investigating. And one of the most prominent features of the Indian Ocean is the monsoon system.
Right. The monsoons are crucial for bringing rainfall to a huge part of the world, especially South Asia.
Exactly. They're a lifeline for agriculture industry and millions of people's livelihoods.
Right.
And there's some evidence to suggest that the IOGL might play a subtle role in influencing the monsoon cycle.
Now that's fascinating. How could a gravitational anomaly affect something as powerful as the monsoons?
It has to do with these subtle changes in pressure that the IOGL creates. Okay.
Remember, the IOGL creates a dip in the ocean surface,
Right.
which alters the distribution of water pressure. These pressure differences can influence wind patterns,
Okay.
which in turn can affect the formation and intensity of monsoons.
Yeah. So we have this chain reaction. The IOGL creates a dip. The dip affects pressure. The pressure influences wind, and the wind impacts the monsoons. It's like a domino effect with each piece influencing the next.
Yeah, that's a great way to visualize it.
Yeah.
And it highlights the interconnectedness of our planet,
Right.
showing how a gravitational anomaly in the middle of the ocean can have ripple effects that extend to the land and the atmosphere.
It really drives home the point that we can't just study these things in isolation. Yeah. Everything is connected, and to understand one piece of the puzzle, we need to look at the whole picture.
Precisely. And that's what makes Earth science so fascinating. It's a constant process of uncovering connections,
Right.
of seeing how seemingly disparate phenomena are actually intertwined.
So the IOGL is a key part of that puzzle.
Yeah. And understanding its role in the monsoon system could be crucial for predicting weather patterns, managing water resources,
Mm-hmm.
and even anticipating potential droughts or floods.
Absolutely. Monsoons are a vital part of the ecosystem in South Asia,
Right.
influencing everything from agriculture to biodiversity.
Yeah.
They replenish rivers, recharge groundwater,
Right.
and support a wide range of plant and animal life.
Oh.
Any changes in the monsoon patterns, even subtle ones, can have cascading effects on the entire ecosystem.
So the IOGL, by potentially influencing the monsoons, could have a significant impact on the environment and the lives of millions of people.
It could.
It underscores how important it is to study and understand these complex systems, not just for scientific curiosity, but for practical reasons as well.
Exactly. The IOGL is a perfect example of how scientific research, even into seemingly abstract phenomena,
Yeah.
can have real-world implications for people and the planet.
It's a reminder that science isn't just about equations and theories.
Mm.
It's about understanding the world around us and using that knowledge to make informed decisions.
And the IOGL, with all its intriguing connections to the oceans, the atmosphere,
Yeah.
and potentially even the very ground beneath our feet, is a powerful reminder of how much we still have to learn.
That's what makes it so exciting. It's like we're peeling back the layers of a mystery, uncovering secrets about our planet that were hidden for millions of years. But we'll have to pause our deep dive here for now. Join us for the final part, where we'll delve into the technology that made the discovery of the IOGL possible and explore what the future holds for our understanding of this remarkable phenomenon. Welcome back to the deep dive.
It's great to be here.
We've been exploring this invisible force field in the Indian Ocean, this gravitational anomaly called the IOGL, and it's been quite the journey from the depths of the Earth's mantle to the surface of the ocean,
Yeah.
and even the air we breathe. We've uncovered how the IOGL formed, how it influences ocean currents, and even its potential role in shaping monsoon patterns. But now I'm curious about the tools and technologies that allowed us to discover this hidden world in the first place.
Yeah. It is incredible to think that we can measure these subtle variations in gravity from hundreds of kilometers above Earth.
Right.
These satellites are really remarkable feats of engineering and science.
Absolutely. Let's start with GRACE, the Gravity Recovery and Climate Experiment. This mission, launched in 2002, consisted of two identical satellites orbiting Earth in tandem.
Yeah.
Okay, we've touched on this before, but remind me again, how did having two satellites help measure gravity? Was it like having a giant set of scales in space?
Well, that's a good way to think about it. But instead of weighing objects, they were measuring the distance between themselves
Okay.
with incredible precision.
So as they flew over areas with slightly stronger gravity, the distance between them would change.
Exactly. Imagine them as a pair of dancers gracefully gliding through space, but linked by an invisible tether. As they flew over a region with stronger gravity, like a mountain range, the lead satellite would be pulled slightly ahead, ever so slightly shortening the tether.
And by measuring these tiny changes in distance, GRACE could map out the variations in Earth's gravity field.
Precisely.
Mm.
And the sensitivity of these measurements was astounding. Grace could detect changes in distance down to a fraction of the width of a human hair.
Wow, that's incredible. So by carefully tracking these minute distance variations over time, GRACE was able to create a detailed map of Earth's gravitational landscape, revealing the IOGL as this prominent dip in the geoid.
That's right. Grace gave us the first truly global view of the geoid.
Okay.
And the IOGL stood out as this massive gravitational valley in the Indian Ocean.
It's amazing how such tiny measurements can reveal such large-scale features. But GRACE wasn't the only satellite that contributed to our understanding of the IOGL, right?
You're right. In 2009, the European Space Agency launched GOCE, the Gravity Field, and Steady-State Ocean Circulation Explorer.
Okay.
And while GRACE focused on measuring changes in gravity over time,
Right.
GOCE was designed to create the most accurate static map of Earth's gravity field ever.
So if GRACE was about tracking changes, GOCE was about getting a super sharp snapshot.
Exactly. It flew at an extremely low altitude, just 255 kilometers above Earth,
Wow.
skimming the very edge of the atmosphere.
That's so cool.
Yeah, and it carried an incredibly sensitive instrument called an electrostatic gradiometer, which could directly measure the differences in gravity between different points on Earth's surface.
Wow, so it was like taking a high-resolution photograph of Earth's gravitational field.
Precisely. And GOCE's measurements confirmed and refined our understanding of the IOGL,
Okay.
showing its exact shape, size, and depth with even greater detail than GRACE could achieve.
It's remarkable how far we've come in our ability to measure these subtle variations in gravity. But I have to admit, all that raw data from the satellites must be incredibly complex.
It is.
How do scientists actually make sense of it all? How do they turn those numbers into meaningful maps and models?
That's where the real magic happens. Scientists use a combination of sophisticated mathematical techniques and powerful computer algorithms to process the data. One key technique is called spherical harmonics.
We've mentioned that term a few times, but I'm still not entirely sure what it means. Is it like some kind of gravitational calculus?
It does involve some complex math.
Right.
But here's a way to think about it. Imagine listening to an orchestra playing a symphony.
Okay.
You hear all these different instruments and melodies blending together, creating this complex layered sound.
Yeah.
Spherical harmonics is like taking that complex sound and breaking it down into its individual frequencies,
Okay.
allowing you to isolate each instrument's contribution.
So they can separate the sound of the IOGL from all the other gravitational noise.
Exactly. They can isolate the signal of the IOGL from the broader gravity field, allowing them to study it in isolation and understand its unique characteristics.
So it's like having a gravitational tuning fork, filtering out all the extraneous frequencies to focus on the one that matters. And once they have that isolated signal, they can really start to analyze it.
Right. They can create
yeah.
detailed maps of its shape, size, and intensity, and even model its evolution over time.
So thanks to these incredible satellites and the brilliant minds that analyze the data, we now have a clear picture of this invisible force field in the Indian Ocean.
Yeah.
But I have to ask, what's next? Where do we go from here?
Yeah.
What are the unanswered questions about the IOGL?
Well, that's a great question. And the answer is that there's still so much more to learn. We're just scratching the surface of understanding this fascinating phenomenon. One of the most exciting areas of research is using the IOGL as a window into Earth's deep past.
So we can use this gravitational anomaly to travel back in time. That sounds incredible. Tell me more.
Yeah, so by studying the shape and structure of the IOGL, scientists can learn about the ancient tectonic processes that created it.
Okay.
Remember, the IOGL is the result of millions of years of subduction plumes and mantle convection. By analyzing its present-day form, we can piece together the history of those events.
So the IOGL is like a fossilized record of Earth's ancient movements, like a geological fingerprint.
Exactly. It's like a time capsule that preserves information about the forces that shaped our planet millions of years ago. And by combining this information with other geological and geophysical data scientists, can create even more detailed reconstructions of Earth's history.
It's fascinating how something as seemingly abstract as a gravitational anomaly can tell us so much about Earth's past. But what about the future? How will our understanding of the IOGL continue to evolve?
Well, one of the most exciting developments on the horizon is the launch of new and even more advanced satellite missions.
Okay.
GRACE-FO, the follow-on mission to GRACE, is already in orbit and collecting data,
Wow.
providing even more precise measurements of Earth's gravity field.
We're getting an even sharper view of this gravitational landscape.
Precisely. And these new data will allow scientists to refine their models of the IOGL, potentially revealing even more subtle details about its structure and evolution. There are also proposals for future missions that would carry even more sensitive instruments, capable of measuring gravity variations with even greater precision.
It's mind-blowing to think about the level of detail we might be able to see in the future. Who knows what other secrets about Earth's interior we might uncover?
The future of IOGL research is full of potentializations. Scientists are also exploring new ways to combine satellite data with other types of geophysical data, like seismic tomography, to create even more comprehensive models of Earth's interior.
It's like weaving together different threads of evidence to create a richer tapestry of understanding. And with the increasing power of computer simulations, we'll be able to model the complex interplay of forces that create features like the IOGL with even greater realism.
Exactly. We'll be able to run virtual experiments testing different hypotheses,
Yes.
seeing how these processes unfold over millions of years.
It's like having a time machine for the Earth itself.
It really feels like we're entering a new era of Earth exploration, where the invisible becomes visible and the mysteries of our planet slowly unravel before our eyes.
The IOGL, once an unknown phenomenon, is now a key piece of the puzzle, helping us understand our planet's past, present, and future.
It really is. And it all started with a simple question.
What's that?
Why is gravity weaker in this part of the Indian Ocean?
Right. That question led us on an incredible journey into the depths of the Earth, through the intricate workings of ocean currents, and into the realm of cutting-edge technology.
The IOGL is a testament to the power of scientific curiosity, the ingenuity of human engineering, and the beauty of our interconnected planet.
It's a reminder that even in a world that seems increasingly mapped and understood, there are still mysteries waiting to be uncovered. And the pursuit of knowledge is a journey that never truly ends. Thanks for joining us on this deep dive into the Indian Ocean Geoid Low. Until next time, keep exploring, keep questioning, and keep wondering about the world around you.